Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 4 Chemistry students. Once again, we're back for chemistry, and I'm Alan. We are still continuing with our topic 3, the periodic table, and the unit 12, that's about the chemical trends in group 17, sometimes called group 7. So in this case, we are coming in for lesson 2, which is about the chemical properties of group 17 elements, as you see on the slide. So quickly, in the previous lesson, that was lesson 1, we just looked at the preparation, and I don't need to talk much about it. All you need to prepare a halogen other than fluorine, you just need the halide ion and the oxidizing agent, whereby the halide will lose electrons, then the oxidizing agent will gain electron. As it loses electrons, then it forms the molecule, depending on which halogen you're having. If you have chlorine, it forms chlorine. If you have bromine, it forms bromine. Iodine, it forms iodine. Fluorine, it is prepared by electrolysis because there is no any other oxidizing agent other than itself. So you don't have any component that can oxidize fluorine or the fluoride ion. So in this way, it is prepared by electrolysis. That is what we covered in the last lesson. Now we are on lesson 2, and we are looking at chemical properties. Having prepared those halogens, they do react. So we are going to be looking at the oxidizing powers of halogen atoms, reducing powers of halide ion, then displacement reaction and other more reactions. But the emphasis will be put on these two, oxidizing powers and reducing powers, for today's lesson. As you looked at in the previous lesson, when the halogens they easily gain electrons, so in that way they have the oxidizing power. Whereas when they gain those electrons, the electrons can be taken away or they can be lost, and that is where we bring in the reducing powers of the halides, as you notice in their preparation. So today's objectives are, you should relate the oxidizing power of the halogen atoms to their reactivity. In simple, how do they react, and how is the oxidizing power related to their reactivity? 2, compare and contrast the oxidizing and reducing powers of these group 7 atoms and anions. In simple, compare and contrast the oxidizing power of halogen atoms and the reducing powers of halides. And that is where we actually have the displacement reaction coming in, but that will be for another lesson. So, going to the first chemical reaction, oxidizing powers of halogens. You remember from your other lessons, when a substance is oxidized, what happens? Electrons are taken from it. And if it is reduced, it has gained the electrons. Focusing on the oxidizing. So, take away electrons, that indicates the substance which has taken away electrons is an oxidizing agent. So what is oxidizing power of halogens? The ability of the halogen atoms to attract and easily accept electrons from another atom. So in the definition, 2 things are considered. To attract and accept, then there must be another atom as the source of electrons. Attract from another atom. So you need to consider those. You must attract, but there must be another atom which is losing the electron. And as such, the halogens are good oxidizing agents. Reason is simple. They only require 1 electron to attain the octet outer electron configuration or to get a full-filled shell. This is an example of chlorine. The single chlorine atom has 7 electrons in the outermost shell with 5 in the p orbital. So it gains 1 electron to have p orbital being fulfilled. In that way, they are forming the halide ion. In this case, it is a chloride. So because of the fact that they simply need 1 electron to be stable, that's why they are stronger oxidizing agents. And let's look at the trends. Trend in oxidizing power and the reactivity. First of all, when we talk of reactivity from what we've just covered, you will notice that halogens easily gain an electron. So that is their reactivity. They react by gaining an electron. And in that process, they are becoming oxidizing agents. That's why we are combining oxidizing power and the reactivity. So what is the trend? The oxidizing power decreases down the group, meaning fluorine is so highly oxidizing than iodine atom. And the same way, the reactivity decreases down the group, meaning fluorine is so reactive compared to iodine. The same understanding because they aim at gaining the stable electron configuration by having full-filled shells. So what is the reason behind that? You notice that we are using same explanation now and again. These are trends. They apply in every group. Down the group, atomic size increases due to more shells being added. So as shells are added, there is more electrons being added, which increases the shielding effect or the repulsion between the electrons. And that repulsion outweighs the increased nuclear charge because each electron added on the atom comes with a proton inside the nucleus. But with more shielding effect outweighing the nuclear charge, then the ability to attract electron reduces. And of course, with the ability to attract electron reducing, the reactivity of halogens also reduces, because if you can't attract, then how will you react by gaining? It becomes very hard. So these two go hand in hand, reactivity and oxidizing power. So what do we finally see? This is something you need to understand. I will compare it with the preparation, as we said. Fluorine is the most oxidizing element in the whole of the periodic table. There is no any other element that can take electrons from fluorine. That's why it is prepared by electrolysis. Electrolysis, you apply electricity, which knocks out electron from the fluoride to form fluorine. So what makes it to have high oxidizing ability is because of small size with high nuclear charge. And at the same time, it's the most electronegative element. So how is the oxidizing powers relate to the reactivity and stability of the compounds formed? You need to know that group 7 have a prominent one stable oxidation state, which is -1, coming as a result of gaining electrons. But if you're having a group 7 bonded to a more electronegative atom, since these are nonmetals, they bond by covalent, by sharing of electrons. So sometimes you can have more than -1 oxidation state. You can have +1, +3, +5, and +7, depending on the number of bonded atoms, and if that bonded atom is electronegative. An example is what you're having in here. Iodine chloride, iodine trichloride, iodine pentafluoride, and heptafluoride. So these are the components, and in this case, as you see, iodine is exhibiting the highest oxidation state. All the outermost electrons are being pulled by fluorine, for instance, if it is bonded to it. Or 3 of the electrons are being pulled by chlorine, if it is bonded to it. And these are the structures. You looked at the bonding in the previous lessons. So these are their structures. Due to the high electronegativity tendencies of fluorine, for it, whenever it bonds, it makes that bonded atom to exhibit the highest oxidation state, like sulfur in here, iodine, as you see. So that is it with oxidizing power. Let's now look at the reducing powers of the halides. Reducing powers of the halides. Yes. Yeah, the halogens have gained an electron to be stable, indicating they are forming halides. These halides, they have a tendency of losing the electron provided there is an agent, there is a substance that is taking the electron, which we call the oxidizing agent. So in that way, they are acting as reducing agents. They are losing their electrons. But remember, they are losing one of the electrons is the one they had already gained. That's why in this case we call them halide ions. They are not halogen atoms. So what happens is, provided you have a strong oxidizing agent, the halide ions will lose electrons. So this takes us to the trend. What is the trend? Down the group, the reducing powers of the halides increases. Meaning, iodide easily loses an electron than fluoride. Let me take here a bit back. Oxidizing fluorine atom easily gains electron than iodine atom. Reducing iodide ion easily loses electrons than fluoride ion. Do you notice that? Same explanation. With reducing power, down the group, the size of the ion increases due to that extra electron added. And so the nuclear charge is not effective at holding the increased number of electrons. In presence of an oxidizing agent, it will take away that electron. So that is the same reason we've been talking of. As shells increase, electrons increase, so the shielding effect will outweigh the nuclear charge, so the outermost electrons can be easily taken away, and that is the explanation behind the trend you see. So let's try and see how exactly that principle works. We are looking at the reducing strength of the halide ions on concentrated sulfuric acid. Something you need to understand is sulfuric acid as a solution, if it is concentrated, it has two prominent reactions. It can act as an acid, as a strong acid, or as an oxidizing agent, provided there is a reducing agent. In this case, we should be using halide ions as reducing agents. So as an acid, it will react with a halide by donating hydrogen ion to form hydrogen halide, or what we call hydrogen. For instance, if you have chlorine, it will form hydrogen chloride. If you have bromine or the bromide ion, it will form hydrogen bromide, depending on the halide you're having. In this case, it will be the acid-base reaction. Sulfuric acid donating a proton, then the halide coming as a base, combining together. So what happens if it is reacting as an oxidizing agent? It will remove electrons on the halide ions as it gains them. So in the process, it will be reduced to different products depending on the strength of the halide ion. In other words, we expect different products when you compare a chloride, a bromide, and and iodide. Let's specifically see that by looking at this experimentation. All right, okay. So we're having our halide ions reacting with concentrated sulfuric acid. In this case, we are using potassium chloride. The purpose in here, it will bring the chloride ions. I want you to notice what will happen. Take a close look. Observe carefully. What do you notice? The bubbling. So, later on, I want us to test the gases that are being produced. First, we need to use the indicator paper. In this case, we're using the universal indicator paper. If you look at it, you notice around pH of 102, it is red or pink, call it pink. Then as the acidity decreases, it goes on changing to blue, which is in the basic. So we are going to use the universal indicator. I want you to take notice on the observation. Observe clearly. What do you see? You see the indicator paper turning to pink. You notice that. So we need to take note of that. What does that imply? The fumes coming out are acidic. So we use ammonia solution to test for the presence of hydrogen chloride. And I want you to notice what will happen when you add ammonia or when you bring ammonia closer to the white fumes. What do you notice? You see, so now in this case, the dense fumes being formed with ammonia, fumes of ammonia and the fumes from the test tube confirm the presence of hydrogen chloride, indicating when we reacted potassium chloride with concentrated sulfuric acid, we have these acidic white fumes. Now let's bring in lead ethanoate. What does lead ethanoate do? It tests for the presence of hydrogen sulfide. If hydrogen sulfide is present, we expect the dirty brown color on this lead ethanoate paper. And if it is not present, we expect it to remain white. Let's see what happens next. Observe clearly. Any observation? No. Now let's use potassium diachromate. It tests for sulfur dioxide gas. Presence of sulfur dioxide gas, it will turn a paper soaked in this diachromate, which will be orange, to white, or it will decolorize the orange color. Let's see what will happen. Any observation? No observation. So that was for potassium chloride and concentrated sulfuric acid. Now let's use sulfuric acid with the potassium bromide. What will happen? Observe clearly. What do you notice? You see the color, the other was white, but this is orange. You see the orange bubbling. You see the orange color of the component. The same procedure we shall do. Use the indicator paper and observe. You see it is turning to pink, implying the fumes are acidic. Add ammonia or use concentrated ammonia solution. What will happen? You see the fumes combining. Then use the hydrogen sulfide. Take note on what will be observed. Still, no change. It's still remaining white. Use the dichromate. Remember, dichromate is for sulfur dioxide gas. In the presence of sulfur dioxide gas, the orange color will be discharged, or it will be decolorized. You notice what is happening around there. So in that way, we had sulfur trioxide. Let's now use potassium iodide. Observe clearly. You see the fumes coming out. You see the yellow solid. You see the purple fumes or the purple coloration. Again, we test in the same way. This is the universal indicator testing for the fumes. You notice it is turning to pink, indicating the fumes are acidic. We're bringing in ammonia also. In this case, we are testing the presence of hydrogen iodide. Then we bring in the hydrogen sulfide. Take note, you see the dark brown. So in this case, potassium iodide it is producing hydrogen sulfide. We're bringing in the dichromate. So you see, we also have sulfur dioxide gas. When you react potassium, okay, now we go back. Okay, so we've observed what happens when we add concentrated sulfuric acid in different salts. Point to note, this experiment needs to be done in a well-installed lab because we need fume cardboards. You can't simply do it in open space. The hydrogen sulfide and the sulfur dioxide gas that are given off are very, very poisonous to our body, so they are not supposed to be exposed anyhow into the environment. For this experimentation to be carried out, you need fume cardboards. So let's exactly summarize what happens. When you have potassium chloride and concentrated sulfuric acid, you will form white fumes of HCl, and the chloride is a poor reducing agent. There is no any other reaction. It's only white fumes due to acid-base reaction. So what happens with the potassium bromide is you will have the white fumes, which are hydrogen bromide, but the presence of the bromide ion, which is a good reducing agent, it will reduce the sulfate in sulfuric acid to sulfur dioxide. That is what you noticed. This is a well illustration in what happened. This is what you noticed. The paper soaked in the potassium dichromate was decolorized. And so this shows us that the chloride is a poor reducing agent. The bromide is at least a good reducing agent. What happens when we used potassium iodide? The same first reaction, acid-base forming hydrogen iodide fumes as you see them. But because iodide is a strong reducing agent, it reduces the sulfate ion to sulfur dioxide gas, to sulfur, which is yellow salt, you even see the yellow salt is in here, and to hydrogen sulfide, which has that rotten egg smell. So in the process, the iodide is oxidized to iodine, which is seen as the purple fumes. You perfectly saw those different observations. So in this case, we are explaining exactly what happens. And these are the equations. You see the yellow salt, which is sulfur. You notice the purple fumes, which is iodine, and the presence of hydrogen sulfide, as indicated by the lead ethanoate paper. So what is the summary? Can we summarize up all that? And the summary is well illustrated in here. What do we see? With potassium chloride, just only white fumes, which are HCl. In this case, that is acid-base reaction. And with potassium bromide, you see the different products. This is the summary of what we looked at. So that is it that we can talk about the reducing and oxidizing abilities of the group 7. Of course, I can't leave you without exercise. In this case, this is exercise 2, as you can see it. Try it and practice as many questions as possible. Thank you for your attendance. Let's stay safe. I want to see you next time. Bye.